power series? A power series is a series of the form summation of Cn times x to the n equals 0 to infinity. So if we plug in n equals 0, we get C0 x to the 0, which is just C0, or we say C naught. That is the typical way that we pronounce that. And then when you plug in n equals 1, you get C1 times x to the 1. N equals 2 gives us C2 times x squared, and so on. X is a variable, and the Cn's are constants called the coefficients of the series. And you can see that because the C's are the numbers in front of the variable x, which we call coefficients. For each number that we substitute for x, the series is a series of constants that we can test for convergence or divergence. A power series may converge for some values of x and may diverge for other values of x. The sum of the series is a function, f of x equals the power series, whose domain is the set of all x for which the series converges. Notice that f resembles a polynomial. The only difference is f has infinitely many terms. So a power series is often thought of as an infinite degree polynomial. As it turns out, power series are extraordinarily useful and therefore extremely important in the study of analysis, differential equations, physics, engineering, etc. The most famous and basic example of a power series is the so-called geometric power series, which is really just a geometric series. So notice that we have the sum of x to the n. So in this case, all of the Cn's that we talked about previously, where we said we have a series of the form Cn x to the n, all of these Cn's here are 1, because there is a 1 in front of the x to the n there. So again, this is the most simple form of a power series. Since this is a geometric series, let's just point out that the first term of this series is equal to 1, and the common ratio is equal to x. Remember, the common ratio of a geometric series can be found by dividing any two successive terms. So for example, I could do x squared divided by x, or I could do x divided by 1. I could do any term divided by the 1 before it, and if I do that, I'm going to get x every single time. Now we know from previous discussions that the sum of an infinite geometric series is equal to a divided by 1 minus r if the absolute value of r is less than 1. Or to say that differently, if r is a number in between 1 and negative 1. So for this particular power series, the sum is going to be 1 divided by 1 minus x. All I'm doing here is plugging these values into the formula. And this will be true if the absolute value of r, which is x, is less than 1, which means x has to be a number in between 1 and negative 1. So to put this a little bit differently, the power series that you see here is equal to the function 1 divided by 1 minus x as long as x is a number in between 1 and negative 1. So we can write 1 divided by 1 minus x is equal to 1 plus x squared plus x cubed plus etc. if x is a number in between 1 and negative 1. So we're going to talk a little bit more about this in the coming minutes here. But basically what you have is a function that has an infinite degree polynomial representation for these values of x. Now, the values of x that you see here is called the interval of convergence. In other words, the power series only converges for these values of x. So if x is any other number, like if x is 2 or -3 or something outside of this interval here, the series diverges. So this power series and this function representation of the power series only makes sense if x is a number between 1 and -1. More generally, we can talk about power series centered at x equals a. So this is pretty much just like the power series mentioned previously, except now we have the series summation Cn multiplied by x minus a to the n. So just to remind you, previously we had talked about a power series being of the form summation Cn x to the n, which would be the same as writing the sum of Cn times x minus 0 to the n. So this power series would be centered at 0. But it doesn't have to be centered at 0. It can actually be centered at any real number a. So when you have a power series of this format, we say it is a power series in x minus a, or a power series centered at a, or a power series about a. All of those mean the same thing. So let's take a look at an example here. We have a power series centered at 3 here, right? Because this is x minus 3 to the n power. And we want to find out what values of x does this power series converge. Anytime you're asked to find the so-called interval of convergence, what you need to do is apply the ratio test. So let's remind ourselves that the ratio test is when you take the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the n term. Or, as I've mentioned in a previous video lesson, we can view this as the limit as n goes to infinity of an plus 1 multiplied by the reciprocal of an. So for us in this problem, the nth term is x minus 3 to the n power divided by n, and the n plus 1 term is x minus 3 to the n plus 1 divided by n plus 1. So applying the ratio test, we will have the limit as n goes to infinity of the absolute value of x minus 3 to the n plus 1 divided by n plus 1. And then we are going to multiply that by the reciprocal of an, which is the reciprocal of this term here. And that's going to be n divided by x minus 3 to the n. Now what we can do is simplify here. So let's notice that you have n plus 1 factors of x minus 3 here, and you have n factors of x minus 3 down below. So these n factors will cancel out all of these except for just one factor. So we will have x minus 3, and then times n divided by n plus 1. Now technically what you can do here when you have the absolute value is you can apply that absolute value to all things in the parentheses since they are all multiplied or divided. So we can say the absolute value of x minus 3 times the absolute value of n divided by the absolute value of n plus 1. Now, of course, the absolute value of n is just n because n is going to infinity, so it is already positive. And the absolute value of n plus 1 is just n plus 1. So really the absolute value only needs to stay on x minus 3 because, again, x is a variable and we don't know what values x can be yet. Another thing to notice is that the absolute value of x minus 3 is independent of n. So this factor here can actually be pulled out of the limit process. And so if we do that, we have the absolute value of x minus 3 multiplied by the limit as n goes to infinity of n over n plus 1. This limit, of course, is equal to 1, and so we end up getting the absolute value of x minus 3 times 1, which is the absolute value of x minus 3. So this is the result that we get when we apply the ratio test. So if we're looking for what values of x does the series converge, we have to remember that the ratio test says it will only converge when the limit that you get is less than 1. So what does it mean when we say the absolute value of x minus 3 is less than 1? Well, we need to remember that this means that x minus 3 has to be a number in between 1 and negative 1. And from there, if we add 3 across the board here, we end up getting 2 is less than x is less than 4. And so we now know that this limit will be less than 1 if x is a number in between 2 and 4. So what that means is that the original series converges absolutely. Remember, the ratio test tests for absolute convergence if x is a number between 2 and 4. Or we can say on the interval from 2 to 4. Now, what about if x is equal to 2 or if x is equal to 4? Well, if you go back to your limit, if x equals 4, for example, 4 minus 3 is 1. And so that is when the limit is going to be equal to 1. And of course, we know that the ratio test gives us no conclusion if the limit is equal to 1. X equals 2 also produces a limit of 1 because the absolute value of 2 minus 3 is equal to 1. So what this means is once you get your interval of convergence, you need to test your endpoints separately. So let's go ahead and do that. So if x is equal to 4, what we're going to do is take that value of x and plug it into our series. When we do that, we get the sum n equals 0 to infinity of 4 minus 3 to the n power divided by n. This gives us the sum n equals 1 to infinity. And I apologize, I wrote 0 there. It should be from 1 to infinity, right? Because you actually can't plug in 0. Anyway, so we get 1 to the n divided by n. And this is equal to the sum n equals 1 to infinity of 1 divided by n. And this diverges because it's the harmonic series. So we know that this diverges when x equals 4. So what this means is that we cannot include the endpoint 4 because it diverges there, and we are only looking for the interval of convergence. So now let's try plugging in x equals 2 to see what we get. So if x is equal to 2, we're going to take the number 2 and plug it into our power series. And when we do that, this power series becomes the sum n equals 1 to infinity of 2 minus 3 to the n power divided by n. This is equal to the sum n equals 1 to infinity of negative 1 to the n power divided by n. And we know that this series converges by the alternating series test. In fact, we can say specifically this is pretty much the alternating harmonic series. So what that means is that our series converges at this endpoint. So what we need to do is go back and make an adjustment on our interval of convergence. We need to include 2 as a part of that answer. And same thing here, if I write the answer in interval notation, we need to be sure to include 2. So the answer is the interval of convergence is all the numbers in between 2 and 4, including the number 2. Now we'll look at a couple of extreme cases. For what values of x is this series convergent? And we have the sum of n factorial times x to the n. So again, we're going to apply the ratio test. Let's identify that the nth term of this series is n factorial times x to the n, and the n plus 1 term of this series is n plus 1 factorial times x to the n plus 1. Now we take the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term. And this is equal to the limit as n goes to infinity of n plus 1 factorial x to the power n plus 1 divided by n factorial x to the power n. And let's make sure we have absolute values around that. Now we can cancel some things here. We know that x to the n will cancel out all but one factor of x on top. And then let's remember that n plus 1 factorial can be written as n plus 1 times n factorial. And so when we divide that by n factorial, like we have here, the n factorial is going to cancel out, and we will be left with just n plus 1. So this becomes the limit as n goes to infinity of the absolute value of n plus 1 times x. Now, of course, we can apply the absolute value to both of those. So we have the absolute value of n plus 1 times the absolute value of x. And the absolute value of x can be factored out of the limit because the variable in the limit is n, right? So x is essentially a constant when we're talking about the limit. And the absolute value of n plus 1 is simply n plus 1. And this is basically the absolute value of x multiplied by infinity. This limit is infinity. And it doesn't matter what value of x you plug in here. Once you plug in a specific number for x, you are multiplying that by an ever-increasing quantity. And so this is always going to equal infinity regardless of what x is. And infinity is always greater than 1. So what this means is that this series diverges for all values of x except x equals 0. Okay, now I'll explain this here, but basically it diverges except for at one value, and that one value is the center of the power series. Now, why does it converge at 0? Well, because if x is equal to 0, if you go back to the original, you have the sum n equals 0 to infinity of n factorial x to the n. So if you write out the first few terms, this is 0 factorial times x to the 0 plus 1 factorial times x to the 1 plus 2 factorial times x to the 2 plus etc. If x is equal to 0, every single term of this series is just going to be 0. And when you add up 0 forever, you get 0. So it's very boring, right? If you plug in 0, yes, it converges, but it's not useful. So one of the possibilities when finding the interval of convergence for a power series is that there is no interval of convergence. It only converges at the center, and it diverges everywhere else. So series like these are just not useful to us. The other extreme possibility when looking for the interval of convergence is what happens in this problem. So here we have the summation of x to the n divided by 2n quantity factorial. So let's identify that an in this case is x to the n divided by 2n factorial. And the n plus 1 term, of course, will be x to the n plus 1 divided by 2 times n plus 1 quantity factorial. And let's just write out that this is x to the n plus 1 divided by 2n plus 2 factorial. So now I'm going to take the limit as n goes to infinity of the absolute value of an plus 1 divided by an, which is equal to the limit as n goes to infinity of x to the n plus 1 divided by 2n plus 2 factorial multiplied by the reciprocal of the nth term. Okay, and so we can see cancellation happens here. We are left with just an x. Now what about 2n factorial divided by 2n plus 2 factorial? Well, let's remember that 2n plus 2 factorial can be written as 2n plus 2 times 2n plus 1 times 2n, and then the rest. So remember, you can always stop a factorial and just put your exclamation point, and that carries out the rest of the terms, or the factors. Now, why do I do that? Well, because I can see that I have a 2n factorial in the numerator, and so those are going to cancel out, and of course we have a 1 left over on top. So this becomes the limit as n goes to infinity of the absolute value of x times 1 over 2n plus 2 times 2n plus 1. Remember, even though we have absolute values around all of this, these are already positive, so we really don't need to have the absolute values around those. Now I'm going to factor out the absolute value of x, and I have the limit as n goes to infinity of 1 divided by 2n plus 2 times 2n plus 1. And this is the absolute value of x times 0, right? Because this goes to 0. Now, no matter what value x is, that number times 0 is always going to equal 0. And 0 is always less than 1. So this is the exact opposite of what happened in the previous example. Here, the limit is always going to be less than 1, no matter what the value of x is. So the interval of convergence here is all real numbers. So x can be any number from negative infinity to positive infinity. And the way we normally write that is in interval notation. And one nice thing about this is that there are no endpoints to test, right? Because the endpoints are infinite. So this means that this power series converges for every value of x that you plug in. Now let's summarize the last 3 examples by giving the theorem involved here. The theorem says for a power series centered at A, there are only 3 possibilities. One possibility is the series converges only when x equals A. And remember, this is the case that we say is pretty much useless to us, right? Because if it only converges at x equals A, it diverges everywhere else. And a diverging series is not useful to us. The second possibility, the one that we just saw in the previous example, is the series converges for all values of x. So this is really nice, right? Because this is an extremely useful series to us since we can plug in any value of x. Now, the most common case is that there will be a positive number r, which is called the radius of convergence, such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. Now, if this is a little bit confusing, don't worry, it's not bad at all. I'll show you in just a second. But this number r is called the radius of convergence, and by convention, the radius of convergence is 0 in the first case, is infinity in the second case, and that radius of convergence will be some other positive number in the third case. The interval of convergence of a power series is the interval that consists of all values of x for which the series converges. Okay? Now, the best way to do this is to just go to a number line. So if you have a power series that is centered at A, whenever you have an interval of convergence, A will be at the center of that interval. And then R is how far to the right of A and how far to the left of A you can travel and still have values for which the series converges. So basically, you end up with all values of x between a minus r and a plus r. And then, of course, the endpoints you have to test separately. So the possibilities for the interval of convergence at the end of the day here is that it's always going to be from a minus r to a plus r, but you might not include either endpoint, or you might only include the right endpoint, or only include the left endpoint, or you might be including both endpoints. It just depends on the series. So again, case 3 of this theorem says that the power series will converge for all numbers x between a minus r and a plus r, where a is the center of the series. It will diverge for all values outside of that. And then at the endpoints here and here, it is unknown if it converges or diverges at those endpoints, and you have to test those separately. So I thought it would be good to come back to example 1 to kind of summarize here. First of all, I want you to notice that in this power series here, the center of the power series is 3, and the interval of convergence at the end was all the numbers in between 2 and 4. So if you draw a number line of that interval of convergence, 3 will be at the center, right, which is the center of the power series. 4 is 1 unit to the right, and 2 is 1 unit to the left. And we're saying that it converges for all values in between 2 and 4. So I'm shading in the interval of convergence here. And at 2, it converged, which is why we have inclusion at 2. And at 4, it diverged, which is why we do not include 4. But in this case, the radius of convergence is 1 unit, right? Because we are traveling 1 unit to the right of the center and 1 unit to the left of the center. So to summarize the examples that we've done so far, remember we talked about the geometric series first. The radius of convergence for that was 1. And the interval was all values in between 1 and -1. In example 1, as we just mentioned, the radius is 1, and the interval is all values in between 2 and 4, including 2. In the second example, the radius is 0, because the only number where it converged was for x equals 0. So this is the one that is not useful to us. And in the third example, the radius is infinity, because the interval of convergence was -infinity to +infinity. Let's find the radius of convergence and the interval of convergence for the following series. So again, we're going to use the ratio test for absolute convergence. AN will be -3 to the n times x to the n divided by the square root of n plus 1. And an plus 1 will be -3 to the n plus 1, x to the n plus 1, divided by the square root of n plus 1, which is the square root of n plus 2. So to apply the ratio test, we are going to take the limit as n goes to infinity of -3 to the n plus 1, x to the n plus 1 over the square root of n plus 2. And we're going to multiply that by the reciprocal of the nth term, which is here. Remember that you can cancel x to the n and x to the n plus 1. We're just going to have an x left over there. For the same reason, we can cancel -3 to the n and -3 to the n plus 1, and we will just have -3 left over. And so what I have so far is the limit as n goes to infinity. I have the absolute value of x times the absolute value of -3 times the square root of n plus 1 over the square root of n plus 2. These can be combined into the absolute value of -3x, which, by the way, is the same as the absolute value of 3x, and that can be factored out of the limit. So we have the absolute value of 3x, limit as n goes to infinity, and then these radicals can be combined under a single radical. And so now we can use properties of limits to move the limit inside of the radical. And we know that this limit in here is equal to 1, and the square root of 1 is 1. And so the value of this limit is the absolute value of 3x. We know the ratio test for absolute convergence says that this power series converges if the limit is less than 1. And this, of course, means that 3x has to be a number in between -1 and +1. And then we can finally divide everything by 3. And we get x needs to be a number in between -1/3 and +1/3. And this is our interval of convergence, but we still have to test the endpoints. So let's go ahead and plug those in now. So if x is equal to +1/3, we're going to plug that in for x in our original series. So we will have the sum n equals 0 to infinity, -3 to the n power, times 1/3 to the n power, divided by the square root of n plus 1. Now, how do we multiply -3 to the n times 1/3 to the n? Well, since they both have the n power, we can just multiply -3 times 1/3, and that's going to be -1 to the n. So we have the sum n equals 0 to infinity, -1 to the n, over the square root of n plus 1, and this converges by the alternating series test. So if you want to pause for a moment here and verify that this converges by the alternating series test, go ahead and do so. What about when x equals -1/3? Well, again, we plug -1/3 in for x here, and that is going to give us the sum n equals 0 to infinity, -3 to the n times -1/3 to the n, divided by the square root of n plus 1, and -3 to the n times -1/3 to the n can be combined as -3 times -1/3 to the n, and this is, of course, 1 to the n, and 1 to the n is 1. And so this is equal to the sum n equals 0 to infinity of 1 divided by the square root of n plus 1. And this series diverges, and it diverges by the p series where p is equal to 1/2, which is less than or equal to 1. Now, I know you may not identify this as a p series, so let's just talk about this very quickly. When you have the sum n equals 0 to infinity, you can change the index to start at 1 if you wish. Okay, so it used to start at 0. If I want to start it at 1, what I have to do is reduce this by 1. So instead of 1 over the square root of n plus 1, it would just be 1 over the square root of n. And you can pause here and verify for a moment that if you start plugging in the numbers 0, 1, 2, 3 here, it will be the same as plugging in the numbers 1, 2, 3, and 4 here. So these series are exactly equal to each other. And this, of course, is a p series with p equals 1/2, right? Which is less than or equal to 1, therefore diverges. So back to our interval now, we know that when x equals +1/3, it converges, and when x equals -1/3, it diverges. So when we go back to our interval of convergence, we are going to include 1/3, but not include -1/3. And so the interval of convergence is going to be all the numbers in between -1/3 and +1/3, including +1/3. Now for the radius, let's graph this interval here. 0 is at the center. 1/3 is your right endpoint. -1/3 is your left endpoint. So again, here is that interval, all the numbers in between here. Okay, so what is your radius? Well, the radius is the distance between here and here. And so clearly that distance is 1/3. So the radius of convergence is 1/3. And for our final example, let's find the radius and interval of convergence for the following series. So once again, we are going to use the ratio test by taking the limit as n goes to infinity of the n plus 1 term. So remember, to get the n plus 1 term, you replace all of your n's with n plus 1. Now on the bottom, when I replace n with n plus 1, I'm going to have n plus 1 plus 1, which is n plus 2. And then we're going to multiply that by the reciprocal of the nth term, which is this. Then we can cancel. We know x plus 2 to the n cancels out all of those except for one factor. 3 to the n plus 1 cancels out all of these except for one factor here. So what we have left over there is the absolute value of x plus 2 over 3 multiplied by the limit as n goes to infinity of n plus 1 divided by n. This limit, of course, is equal to 1. So we have the absolute value of x plus 2 over 3 times 1, which is the absolute value of x plus 2 over 3. And we know that the ratio test tells us this converges if this limit is less than 1, which of course means that x plus 2 over 3 has to be a number in between negative 1 and positive 1. Now to solve this, I'm going to multiply all three parts here by 3, which gives us negative 3 less than x plus 2 less than positive 3. And finally, I'll subtract 2 from everything, which gives us negative 5 less than x less than 1. So this is our interval. If you draw this on a number line, here's negative 5, here's 1. What number is right in the middle between these two? Well, it's negative 2, right? It's 3 units this way and 3 units this way. So we can see the radius of convergence is 3. Now for the interval, don't forget, you still have to test your endpoints because we don't know what happens here and here. So to test those, we'll do those separately. So if x is equal to 1, we're going to plug 1 into the original series here, which is going to give us the sum n equals 0 to infinity, n times 3 to the n divided by 3 to the n plus 1. So again, when I plug in 1 here, I just get 1 plus 2 is 3. We get simplification here. This cancels with some of those. And this is the sum n equals 0 to infinity of n divided by 3. And this diverges, okay? And it diverges by the divergence test because if we take the limit as n goes to infinity of n divided by 3, we get infinity, which is not 0 and therefore diverges by the divergence test. Now what about when x is equal to negative 5? So if I plug in x equals negative 5 into our original series, that means that we are going to replace x here with negative 5. Negative 5 plus 2 is negative 3. So we get the sum of n times negative 3 to the n divided by 3 to the n plus 1. And we have to be a little bit more careful here. I'm going to write negative 3 to the n as negative 1 times 3 to the n, which is negative 1 to the n times 3 to the n. And then we're dividing that by 3 to the n plus 1. This is going to cancel out those there. And we end up getting the series negative 1 to the n times n divided by 3. And this also diverges and also by the divergence test, because if we take the limit as n goes to infinity of this nth term, this limit does not exist because this is going to infinity and then the negative 1 to the n makes it alternate between positive and negative. So both of the endpoints fail, right? They both give you a diverging series. So now if I go back to my interval of convergence, we are not going to include negative 5 and we are not going to include positive 1. So in essence, this is our interval of convergence, or I could write it like this, which is the way I prefer to write it. And that concludes this video lesson.